We will now move on to the program, ladies and gentlemen. And of course, this will be for our first keynote speaker of the day, Mr. Al Geist. Allow me to share a little bit more about him. Mr. Geist is a corporate research fellow at the Department of Energy, DOE, Oak Ridge National Laboratory. He is the He is the Chief Technology Officer of the National DOE Exascale Computing Project, which is developing technologies for solving computational grand challenges, and also the Chief Technology Officer of the Leadership Computing Facility, which is delivering the first exascale computer in the US of A, called Frontier. Without further ado, ladies and gentlemen, do join me in welcoming Mr. Al Geist, who will be delivering his keynote speech on the first exascale supercomputer in the United States of America. Mr. Geist, please.
Good morning. And I want to thank the organizers for the invitation to speak at Supercomputing Asia 2022. And I apologize that due to COVID restrictions, I'm not able to be there in person to present this exciting talk about the first exascale computer in the USA. And I'm waiting for the slide to change. Can I see the next slide? Thank you. So I work at Oak Ridge National Laboratory in the USA, and one of the missions there is to provide world-class computational resources to solve the most computationally intensive global problems in energy and materials, the environment, and health. And as you can examine our journey from petascale to exascale, you see that it's actually been steady progress across that range, not a big leap to exascale like we thought it might. So as you see in the diagram, back in 2009 with Jaguar, it was about a 2 petaflop computer, a little more than that. And in our next generation, Titan was about a 20 petaflop computer. And in the generation after that, the one we're running today in production, Summit, we're at 200 petaflops. And now, just delivered, is the Frontier computer at 2,000 petaflops. So you can see that each step in each generation was about an order of magnitude step, and each step towards exascale. But there were big leaps that we made, and we can see that in this next diagram. So one of the biggest things that we worried about since 2009 was the biggest concern reaching exascale had been energy consumption. And we can see that in the diagram here on our right. So you can see that Jaguar that we saw on the diagram there in 2009, if we had scaled that up to an exaflop, then it would have required 3 gigawatts of energy to run. And so exascale was actually made possible by a 200x improvement in energy efficient computing. And you can see that in our journey. So when we went to Titan, suddenly you see a 10x improvement in energy efficiency. And that was due to moving to using NVIDIA GPUs in that supercomputer. As we moved to Summit, it decreased further, and the way that architecture was designed to allow that was actually using multiple GPUs per CPU. We had 3 GPUs per CPU in Summit. We were down to about 65 megawatts per exaflop in energy efficiency. And then Frontier has taken the next step again with 4 GPUs per CPU and the incorporation of a lot of energy efficiency technologies from AMD, so that Frontier now achieves 14.5 megawatts per exaflop. But there's actually additional energy savings that we needed to work on, and that is because Frontier consumes about 29 megawatts. You still need to cool your data center back down. And so we achieve additional energy savings by using warm water cooling in Frontier 32C. And that allows our ORNL data center to have an incredibly low PUE of 1.03. Now, I want to talk a little bit about supercomputing for all, because that is our theme here for SCA 2022. And what I've done is to try to contrast some of these largest supercomputers. And so I've plotted the compute capability of the top 50 supercomputers and their peak petaflops on this diagram. And you can see that it looks almost like the axis of a graph. One is right down there near zero and one shoots straight up. What we see is that the top few supercomputers are sort of in a class all their own and reserved to solve some of the biggest computational challenges in the world. So you see Fugaku on there, and there's been several really interesting talks here at SCA this year about some of the very nice work that they have been doing on that supercomputer. We see Summit, and I'll be mentioning a couple of things that we've been doing there. I put a question mark on here as a placeholder for some of the interesting Chinese machines. And there you can see Frontier at the very upper levels. But I also want to talk about the largest cloud supercomputer. So in 2021, the Azure Voyager has some very, very nice properties. It has the ability to serve thousands of people and to be much more accessible than these very top-level supercomputers. So one way to think about the cloud is it's like a 747 airliner. It's satisfying the travel needs of millions of people every year. Whereas we might think of these top supercomputers are more like Apollo. It's like no amount of 747s would ever get you to the moon. But that also leads to an interesting second problem that we wanted to make sure that we addressed before we made it to exascale. So as supercomputers got larger and larger, we expected them to be more specialized and very limited to just a small number of applications that could exploit their growing scale. Many people were predicting this to be the case, but in our journey to exascale, we found that the Summit architecture, which has just a few large memory multi-GPU nodes, actually was able to excel not only at the advanced simulations traditionally solved by these large supercomputers, but also was very good at solving high-performance data analytics, as well as artificial intelligence problems. And a couple of the examples that I show here on this slide, one in deep learning, where Summit was able to achieve a sustained throughput of 1 exaops. So this is reduced precision, half precision calculations, trying to learn to detect extreme global weather patterns. And then in data analytics, an example of Summit being able to excel in things other than simulation was an application in comparative genomics, where it was able to achieve 2.3 exaops in a mixed precision calculation. And that was actually the winner of the 2018 Gordon Bell Award. So given that we had stumbled onto this very effective architecture, the Frontier exascale computer uses and actually improves on Summit's successful architecture. And in the next slide, we'll go through more of those details. So first off, I just want to kind of point out that the Frontier has a lot of really extraordinary engineering in it. I've been doing supercomputers for all those years that you saw in the first slide. And Frontier is really amazing in several ways that I'll point out today. It's built by HPE and powered by AMD. And as we see in the left column about the system, so this is a 2 exaflop double precision machine. And they've been able to pack that much performance into just 74 compute racks. It's very amazing. And to only consume 29 megawatts of power. Each one of those racks holds 128 AMD compute nodes. And everything in that compute rack is water cooled, even the memory chips, even the communication chips, and obviously all of the CPUs and GPUs in there. Everything inside of that cabinet is water cooled. There are only 9,408 nodes in a 2 exaflop computer, so very small number of nodes given the performance of this machine. And each one of those nodes, as we see in the right column, has one AMD Trento CPU, 4 AMD MI250X GPUs. And in addition, it has half a terabyte of DDR memory. It's got another half a terabyte of high bandwidth memory on every node. And all of that memory is coherent across all the GPUs and CPUs. They can all see all of that memory. And then in addition to that terabyte of memory on the node, there's an additional 4 terabytes of non-volatile memory on that node. And it's all connected. All the GPUs and CPUs on the node are fully connected by AMD's Infinity network. There are a few other interesting things, though, that occurred. It was quite the challenge for Frontier to be built and delivered to Oak Ridge because in the middle of COVID, there was this chip shortage. Frontier actually has about, a little over 59 million parts in it. And when HPE and AMD went to order all the parts to build Frontier in 2021, there were about 2 million parts out of the 59 million that the manufacturers simply could not supply, that they were short in those. And so there was a heroic effort by those two HPE and AMD teams calling up electronics warehouses and saying, do you have any of these? We would like 10,000. And they'd say, well, we might have 500 of them. We'll buy them all. Okay. They'll call up other manufacturers and say, do you have any of these power supplies, or do you have any of these voltage regulators? And they might say, yes, we do. And we haven't been able to build our product because we've had a chip shortage of something else that's holding us up. And so between those two companies and doing all of this extra effort, we actually were able to deliver Frontier. You can see there on the picture on the left, that's an actual photograph of the front of Frontier. In the inset in red, you can see the last cabinet that was being rolled into place back in October of 2021. And each of these cabinets weighs 3,630 kilograms without the water in them. So one of the things, the challenges that we actually had to take out all of the computer room floor in our data center and replace it with a much stronger floor to be able to hold up the cabinets that were in that are in Frontier. And you can see diagram of our computer center there on the right. So another amazing thing, again, it's only 74 cabinets, and those 74 cabinets only take up 372 square meters. So in fact, our data center we designed it much larger, thinking that a 1 exaflop computer, which is what we had originally thought we would get, would consume that data center. In the end, we got a 2 exaflop computer, and it only consumed a fraction of the full size of our data center. The other two things I wanted to quickly point out here on this slide is the data storage that goes with Frontier. So you can see up in the corner, again, a very compact data storage center that holds over 716 petabytes of storage available to the science users of Frontier. And then something I'll mention in the very last slide, so that I'll point it out here, you can see a very small circle, a test and development system. So it's just a small fraction of Frontier that's sort of carved out for that. And I'll talk about the users that are on it right now today. So one question that usually comes to mind when people hear about this system is, how can I get to use it? Who gets to use Frontier? So all of the supercomputers at Oak Ridge National Lab over the years they're managed as an instrument for scientific discovery. So think of them more much like the Hubble telescope. So it's not a cloud model. Only a few get to use it each year. So think about the Hubble telescope. It can only point in one direction at a time. So only a few people can get to use it. And so you have to be very selective. Now, it turns out that these big computers are literally solving the biggest problems in the world. And to make sure that they are used for the most important problems, there's actually an annual competition to get time on this instrument, these supercomputers. And it's very competitive, and it's open to researchers from all around the world, just like scientists that want to use these telescopes. These proposals are evaluated by panels of scientific experts who go through, and only the most important and timely science gets selected that year. For the winners, there is no cost to use the instrument, just like the people who use other scientific instruments like the Hubble telescope. They don't pay for it because in some sense, we think of their contribution to science, the science advancement, helps all of mankind. But it also leads an interesting challenge for us, and why I mentioned earlier about the need for Frontier to be able to solve a wide range of problems, because you can see that Frontier can't be designed to solve just one particular problem. Every year, we get a new set of problems that scientists want to solve. And so on this slide at the bottom, I've actually given details for people who would be interested in this annual competition. So it gives the details about that competition and how to apply for it. And so here are some of these important and timely science problems that we've looked at in the past few months. One is, as you might imagine, being timely, is examining the COVID-19 diverse systems. So we used the Summit supercomputer, which is our production supercomputer now, to do genetic analysis of 18,000 patients to help provide a model to explain all the diverse symptoms that COVID patients seem to have, and to try to understand why some patients have symptoms that last for months afterwards and others recover. And what this study was showing is that the COVID-19 infection invades the body through the ACE2 receptors in the nose. We knew that without this particular study. The virus then proceeds entering cells, multiplying and entering cells and all other places in your body where the ACE2 receptors are present, such as in the heart, the kidneys, and blood vessels. And even now, I read a report just last week where they were saying there were cases where doctors are finding people who had very mild cases of COVID, but now had certain damage to their heart that they weren't even aware of because of the way COVID works. But what this study found by looking at these genetic markers is that COVID does something very clever. It actively hijacks the body's RAS system and tricks it into upregulating ACE2 receptors throughout your body. So you actually find places like in the lungs and nervous system where you normally would not have the COVID be able to attack. It actually upregulates to try to allow it to do that in certain people. And so that's how we find these diverse symptoms, because as COVID starts to hijack this RAS system, it can cause certain people to have very different things to happen. And long haul, if this RAS system gets out of whack, it can make really bad problems for them over the long term, even after COVID has actually disappeared from their body. Another big important problem is climate change. I think we all know and have seen through the various storms and floods and droughts around the world. And Oak Ridge Supercomputers, from our longtime users, all of the computers that I showed on the first slide have done these climate simulations of the entire planet for 50 years into the future. What are we using it for in just the last year? We're really using these supercomputers to investigate the effectiveness of different energy policies that people have proposed before we go and do something drastic to our planet. So for example, trying to understand what would be the effects of different carbon capture methods. What would be the effect of the reduction or elimination of coal power plants? What would be the effects of having electric cars everywhere? And to do many of these what if experiments, we actually have to make many full machine simulations. So that's why we need such large computers dedicated to just a small number of people, so they can get enough computing power to do these simulations to understand the effects on the planet for many years into the future. And as we look at those simulations, we study them for what are the effects on the populations in different areas, and also what are the energy requirements around the world as these things occur. And so when it comes to energy requirements, that's another big area that we explore on this computer. There's solar energy. We do a lot of modeling of organic and inorganic materials to try to improve the photovoltaic efficiency, but also to try to find materials to lower the cost of solar energy. Similarly, we do simulations in fusion, in particular, trying to model the plasma inside of the ITER fusion demonstration that's being built in France. And that's the plasma is the pink in this inset picture. And one of the, I guess, interesting, but also a little bit scary things that we find, and again, the reason why you use a big supercomputer to do this before you build this facility, is that the plasma is not just held in a donut in the middle by these large magnets. The plasma will actually start going around like a racetrack inside of this fusion reactor as it's running. And as it runs around, there will be turbulence, and the spinning ion particles produce magnetic fields. Well, they're being held in by magnetic fields. And so there's the possibility to produce very strong localized magnetic fields due to these turbulences that can happen in there. So you have to be very careful that you can make sure that the plasma remains contained. And on my last slide here, in wrapping up, I wanted to talk a little bit about some of the early science runs on Frontier. These will be runs that happen before this competition that I mentioned gets started. And this really starts about 5 years ago. There were 24 science teams that were chosen for potential early use of the first exascale computer in the USA. And in fact, we didn't even know that would be Frontier at the time that this project, the US Exascale project, started. But at the time, there were 24 that were selected, and now those have actually been given access to that Frontier test and development system that I showed on the earlier slide, a small carve out of the size of Frontier. And they're busy working on the various application portfolio that you see here. So climate change, they're looking at different carbon capture and metagenomics type of problems. In clean energy, they're looking at wind turbine. They're looking at small modular reactors. In healthcare, they're doing a lot of AI code development for cancer research. Of course, there is the traditional scientific discovery type of problems that you might imagine these science teams and these large computers would be used for, like trying to understand the fundamental laws of nature or to predict new advanced materials. But there's also interesting work going on in manufacturing. So at Oak Ridge, we actually have very large 3D printers that can print in both metal, titanium and steel, as well as in carbon fiber. And we've even built an entire car. Actually, we built 3 of them just as demonstrations at the lab, kind of to show off. But more than anything else, the key here from this science teams are trying to make sure, though, that when you make these parts in 3D with these printers, that they actually have the correct strength and qualities that are necessary. So can you build quantifiable metal and carbon fiber parts in these ways? So you have to model exactly what's going on inside the printer. So there's a lot of really exciting work. They've all been told that they're going to get the access to the full Frontier system for early science in July of this year. And so I expect at SEA 2003, and I really want to invite people to come there, that we will hear about the discoveries that these teams will have achieved in that time frame. With that, I want to thank you for your attention and welcome you to the SEA second day.
Thank you very much, Mr. Geist.